In this recording, we will be talking about one of the artificial intelligence techniques or algorithms, which is neural networks. Neural networks are forecasting methods and they are based on simple mathematical models of the brain. They allow complex, non-linear relationship between the response variable and its predictors. To go deeper into this, neural networks are used for predicting cross sectional data. It's also used for the time series forecasting, especially in financial forecasting. And when external information is useful, we use a neural network. Also, neural networks can be used to generate numerical and binary forecasts, not just numerical, both binary and numerical forecasts. A neural network algorithm is based on a model of biological activity in the brain, where the neurons are interconnected and learn from the experience as you see it in this figure. Neural nets are highly data driven and can become computationally expensive, and their structure supports capturing complex relationships between predictors and the response variable, and setting them, both of them requires little user input. It's kind of automated. So the price is that neural nets are considered a black box in a way that the relationship they capture is not easy to understand, and they are considered good candidates for the automated predictive tasks. In terms of the performance of the neural networks, the forecasting literature includes inconclusive evidence regarding the performance of the neural networks for the time series forecasting, and many reported that it outperformed other methods in a very few cases, while in others their performance was found to be inferior. So it's not considered like a strong model to be used initially. However, it was found that the performance of the neural networks is more beneficial with high frequency series. If you have like hourly series, daily series, or maybe weekly series, so this considered a good candidate data set to be used for the neural network. This is compared to the low frequency series. Neural network may not perform as other techniques. Finally, it can be combined with other methods to produce unsampled forecasts. We have seen in the linear regression can be used for modeling nonlinear relationship between the predictors and the outcome variable by using transformations like log of y or creating derived variables from the predictor variables such as t squared or taking the sign. Neural networks offer further extension of linear regression by creating multiple layers of derived variables, and the network links the predictors and the outcome through a sequence of layers. In each layer, in each layer, some operation is performed on the input information to produce an output, and the output of one layer is considered to be the input into the next layer, and so on. And neural networks consist of three types of layers. The first layer is the input layer. The input layer accepts input values of the predictor, can be numerical or binary. Then we have the second level, we have one or more hidden layers. And this receives input from the previous layer, which is the input layer. Again, we have an input layer, then we have one or more hidden layers. And these hidden layers, they receive inputs from the previous layer and performs calculations on those inputs and generate the output. Then we have an output layer. The output layer receives inputs from the hidden layer, from the last hidden layer, and it produces a predicted values, whether these values are binary or numerical. These are just two examples about a neural network model. And if you see in the left, I'm going to speak about both of them. In the left, we don't have a hidden layer. In the right side, we have a hidden layer, one hidden layer. So each layer contains nodes. We have to know that each layer contains nodes. These are nodes. This is node. And these nodes are circles. And each node is a variable. So this is the first input, one variable, this other one, this other one, and so on. So the input layer nodes are the original predictor of variables, these guys. And this is the simplest network. The simplest networks contains no hidden layers and are equivalent to linear regressions. So this is like linear regression. So this figure shows the neural network version of the linear regression with 40 predictors, 1, 2, 3, 4. And these are the weights. This is beta 1, beta 2, beta 3, beta 4, right? This is like yt equals beta naught, obviously, beta naught plus beta 1 times x1 plus beta 2 times x2, beta 3 times x3, beta 4 times x4, right? So these are the weights. We call them the weights. And the output is a linear combination of these. So the weights are selected in the neural network. If you ask about the weights, they are using learning algorithm that minimizes the cost function. What is the cost function? Like MSE. MSE is a cost function. So the idea is to minimize these errors. Okay. So of course, in this simple example, we can use linear regression, which is a much more efficient method of the training data, the model. Once we add the intermediate layer with the hidden neurons, the neurons or the network becomes non-linear in this case. And this is known as multi-layer feed-forward network, where each layer of the nodes receives input of the previous layer, and the outputs of the nodes in one layer are the inputs to the next layer, as we mentioned. So this receives inputs from here, this one receives the input from these, right? The inputs to each node are combined using a weighted linear combination. So look at this one, it receives weight from first input, weight from here, another weight here, and this one. So they have different weights. The same as this guy. This guy receives 4 different weights. This guy receives 4 different weights. So it's a linear combination of these. This one linear combination of these. This one is a linear combination of these, right? So different betas. So this is beta 1, beta 2, beta 3. This is beta 4, beta 5, beta 6, and so on. You can give them names, and as you see here. So the result is going to be a modified, or when we finish from here, we may modify this by a nonlinear function. It's called activation function. The activation function, the most used activation function, the sigmoid one, this one. So we ended up like calculating, it's like a transformation. We transform the output. So we got the output, this is the output for the Z at the end. We got the J. Then we get the last output we transform this one using the sigmoid function. So these are examples, other examples. Linear regression, logistic regression, and autoregressive models can be written as neural networks that like hidden layers, as we see in the left. It is important to notice that because in practice the best performing neural network is often the simplest one. So this is important. So the simplest one, we are looking for the simplest one all the time. If you did not find the answers that we're looking for, we move to the complex one. The simplest one, the one that has no hidden layers. So look at the figure on the left. It displays what? A neural network diagram for what? A linear or logistic regression with 3 predictors, right? And with dummy variable, 2 dummy variables. Is it weekday or no? Is it Saturday or no, right? The idea is to capture the additive weekday, Saturday seasonality patterns. Is it Saturday or Sunday? This figure, for example, shows the neural network for the autoregressive 3. This is the input. My inputs are yt minus 1, yt minus 2, my yt minus... These are the lagged values. So yt is the linear combination of these b naught plus b1 beta 1 times yt minus 1, beta 2 times yt minus 2, plus beta 3 times yt minus 3. And this is, if you remember, this is AR3, autoregressive order 3, right? However, the last figure, if you look at the figure in the right, note that the neural net can include multiple output modes. So these are multiple nodes here. In the context of the time forecasting, we use this to produce forecasts of different horizons. So that scheme is based on a roll forward forecasting, where the forecasts of the times t1, t plus 1, t plus 2, up to t plus k are based on the series moving forward one period at a time. And maybe additional hidden layers can be added in the figure to further increase the complexity of the relationship between the input and the output layers. So in forecasting, YT here becomes lagged input because it's the last known observation at the time you predict the future values. So this is why it is the last thing that we know. The idea is to forecast what's happening in the next day or next hour or whatever, right? As an example, two researchers in their study found that for forecasting annual Japanese tourist arrivals in Hong Kong, they used a neural network, and the neural network outperformed the naive forecasts and the linear regression and the moving averages and the smoothing techniques, exponential smoothings. So the input layer of their study was what? The average hotel rate, foreign exchange rate, and population and marketing expenses, and gross domestic expenditure. And all of these, if you just think about them, all of these are external information. The last thing I would like to talk about is the pre-processing. The pre-processing before we do the neural network, we will not be talking about the details of these layers and how they calculate, etc. But we have to have a general understanding of what's happening in the neural networks. So before we conduct the modeling, there are two things we have to pay attention to. The first one is the pre-processing. Therefore, the pre-processing issues would be considered before running a neural network. As in the regression models, we can create predictors such as lagged versions of the time series, because lagged version, we can have not just lagged versions of the time series, we can have lagged versions of the external information or seasonal dummies and the time index to capture the trend. These are then used as inputs for the network. The other thing that we need to look at when creating lagged variables that will be included as predictors, we have to think about missing values. So we have to remove the missing values of the rows. If you have rows that contains missing values, these should be removed. The third issue that we need to look at is the scaling. So networks performs best when the predictors are scaled, the predictors and the response, both of them, predictors and the response variables are scaled. What's the scale? The scale of 0 to 1 or negative 1 to 1. And in the time series context, the series itself as well as the predictors should be scaled before running the neural network model. And this can be done by subtracting the mean or the value, the mean from the value, then divide by the standard deviation. In this case, we're going to get a value between negative 1 and 1. And this can be done automatically in R. The last issue is about removing trend and seasonality. Is it something that we have to do or no? In literature, there are mixed of reports about this. Do we need to do that or no? Do we need to remove it or no? Some researchers claim that the neural networks can automatically account for the trend and seasonal patterns, so there is no need to remove them. However, substantial empirical evidence has shown that deseasonalizing and detrending improve the performance of the neural network. So technically, maybe you want to think about we have to remove them. So these are the four issues that we have to look at before we start building the model. The second thing that we want to talk about is the user input, because as we said, we have a little flexibility in terms of building these models, just we have to have some inputs as a user input. So to run the model or to run the neural network, you as a user must determine number of inputs, number of hidden layers, number of nodes per hidden layer, and the activation function, which is, as we said, it's a mathematical function. We apply it in each neuron or node in the hidden layers and sometimes in the output layers. And what does this do? The activation function, it controls how many or how the neuron transform its input into output. It's a transformation function. And finally, we have to look at the output, number of output nodes. So for the number of input nodes, technically is equal to the number of the predictors, because you have some predictors. So this depends on the problem itself. The more input nodes, if you have more predictors, so less time periods for the network to train on. This is important. So it's recommended to use the important input variables, not all of them. Just make sure that we are using which ones are more important. Why is that? Because number of the input predictors has a significant impact on the performance of the model. The second thing we need to consider or we need to input is number of the hidden layers. Number of the hidden layers affect the level of the complexity. So how many levels do we need to have? 1, 2, 3, etc. Right? So this will determine the level of the complexity of the relationship between the input and the outputs, as we said. So we recommend, or the literature recommends, that typically we have 1 or 2 layers. They're going to be good. They are sufficient because using too many layers may cause overfitting. On the other hand, if you use too few heads or layers, may lead to underfitting. For the number of nodes per hidden layer, so we have hidden layers and we need to specify number of nodes. How many nodes do we have to be there? This requires trial and errors. If you use too few nodes, this may lead to underfitting. On the other hand, if you use too many nodes, it's going to lead to overfitting. So comparing training and validation performance would be helpful in determining the appropriate number of nodes per hidden layer. The choice of activation function, the most common one used is, as I said, is the S one, which is the sigmoid one. The last one, I did not write it down here, which is number of outputs nodes. That one depends on number of forecasts that we want to generate. And the problem here, some softwares, they are limited to just using a single output. So this is everything for the neural network. After that, we are going to jump into the example in R.